go through this introductory lecture to this course. You know, the course code is the title of the course is Mechatronics Workshops. So under this workshop, you have to do practice workshops. But this is the first course on mechatronics, basically. So for the first time, you are going to be introduced what is mechatronics. But on top of that, I'm trying to introduce also another definition, which you are supposed to learn at the beginning of the your career here. But often, sometimes it is missed. This is definition of engineering. You are learning engineering, but I believe, and so far I know, many of the students do not know what is the definition of engineering. So you can see here, this is one definition from ABET, Accreditation Board of Engineering and Technology. An innovative and methodological application of scientific knowledge and technology to produce a device, system, or process which is intended to satisfy human needs. So here you can see inside the definition, there is no term engineering. The term is knowledge, technology. And what kind of knowledge? Scientific knowledge. And what do we use with this knowledge? We produce device like your handphone, like a computer, like a printer, everything. These we call the devices or systems. System, you can say the water supply system, gas supply system, or processes. So processes I will show later in a video. So how do we make things and what are the steps we follow in making the things? Those are known as the processes. Another definition that is also by ABET, the profession in which knowledge of the mathematical and natural sciences gained by study, experience, and practice is applied with judgment to develop ways to utilize economically the materials and forces of nature for the benefit of mankind. This is a very comprehensive definition of engineering. As a profession, what the engineers actually do. We need mathematics, we need natural sciences, physics, chemistry, all these courses, and also we need experience, how the things around works, how people behaves. Those are the part of the experiences, and apply this with judgment to develop system economically. This is one of the important elements of engineers. When we develop something, we consider the economic part of it, whether it will be affordable to the people and whether it will contribute to the economy generation. And then also the materials and forces of nature. And at the end, why we make all this for the benefit of mankind. So this is what is basically the definition of engineering. So in short, we can see we use knowledge of mathematics, science, and experience to develop devices for the benefit of mankind. So in short, if you say, this is the definition of engineering. So it is very clear when you want to study engineering, mathematics is a very crucial element, and next to the mathematics immediately comes the science. So whatever you are studying under the course title of electrical circuits, and then dynamics, statics, they are basically under the science, and its major science is basically the physics. And also we need chemistry in some of the cases. Like biotechnology, they need a lot of chemistry. Chemical engineering, they need a lot of chemistry. So this is in general what is engineering. And here you see there is a difference between engineers and scientists. Scientists, you understand very well, the physics, chemists who are working around, they are the scientists. The scientists discover the world that exists. That means what is happening, why the Earth is rotating about the sun, or how the solar system is organized. So these are basically the discoveries of the science. Engineers create the world that never was. So there was no car on Earth. So engineers created the car. There was no handphone on Earth. So engineers created the handphone. And When we talk about the mechatronics, it is a special branch of engineering we call the integrated branch. We had traditionally, if you go back to the history of engineering, engineering started with basically civil engineering. Civil engineering, before it became in the civil engineering, engineering used to be known as the military engineering. Military engineering was basically the civil engineering, developing the trenches, roads, and what do you call the, how to cross the rivers. These were the activities of the military engineering. And thereafter, the military engineering has been divided into three groups. One is civil, then electrical, and mechanical engineering. Those we call as traditional engineering. Civil, electrical, mechanical, they are known as the traditional engineering. The synergistic combination of mechanical, electrical, and computer engineering, later computer engineering is known as the mechatronics. That means we combine these disciplines, basically mechanical, electrical, and computer, in a complacent and compliant way so that they match well with each other. That way, if we make combine together to achieve a goal, so that is basically mechatronics engineering. And mechatronics engineering, we give the emphasis on product design that involves multi-physics domain. Just to mention, what is the physics? Physics is the electricity, then magnetism, and then statics, dynamics, fluid, heat transfer. These are the physics. So here we need to know these different physicses to put together to come up with the products. So if you see the domains and subdomains at the center, here we have the mechatronics. And mechatronics, you see so many involvement. It involves control system, electrical system, mechanical system, computer, and then where we apply everywhere: automotive, aerospace, medical, defense, consumer product, manufacturing, everywhere it is there. So let us have a look at an integrated product in mechatronics. Let me see whether it works. Can you hear the sound? Plastic injection molding is the most common method for mass manufacturing of plastic products. The principle is simple. Inject the melted plastic material to the melting material and then solidify it into the solution as the temperature of the cavity. The process involves three parts: injection machine, plastic injection molding, and plastic pellets. Plastic pellets, copper, are filled into them. Then the sample transports the pellets forward and advance rapidly from the plastic pellets. As the pellets are melted, rotates through a gradually. Once enough melted plastic is in front of the screw, the screw injects the melted plastic into the melted plastic. The melt temperature is determined by the temperature controller. It is much lower than battery temperature, so the melted plastic solidifies in less than a minute. The quantity of materials and white, the melted makes the push bar of injection. The injector point at the part is injected. The melted cleanses and those last remains. So from this video, we can see the product, which is the injection molding machine. Here, the plastic pellets are being molten, so we need to apply heat. It becomes a liquid, and then we transfer it with a mechanical system. It goes to a molding box where we cool it again to solidify. Then, with sequential operation, we remove it and we repeat the cycle. So you see here, we have the heat transfer, we have the fluid mechanics where the liquid is flowing. Heat transfer, we are heating to melt it. Then mechanical system, we are moving it. And to move it, we need the electrical motors. And to do its sequential operation, we need the computer. So you see, this is an example of a mechatronics product. And we combine, of course, in optical way, so that optimal way, so that the product is economical. So mechatronics nowadays has become a reality, specifically in the 20th century, due to the following development. Before this, mechatronics was there, but we used to tell them electromechanical engineers. So electrical and mechanical was there. The software component was not that intensive. Nowadays, because of the computer and the microcomputer association, so we have electrical, mechanical, computer, and software. Soul of mechatronics system is its control system. Mechatronics is more than control engineering, however. Control system is how do we control things to achieve a desired goal. Like when we are using the simplistic control in our electrical iron, we have a knob we set for a particular clothing. That means it will maintain a particular temperature. So it is a very simple control, which we call the on-off control. That is the way we maintain a temperature. But in modern product, the control needs very sophisticated, which cannot be that simple, and which needs computer or microcontroller to be in the picture. So you see, now when we talk about the control, last time there were control engineers. Still there are engineers who are known as the control engineers. Their main job was when the mechanical systems and everything is designed, then those are translated to those control engineers. They would come up with the mathematics and will develop the controller. That was the way they used to work. But mechatronics are integrated. They are mechanical engineers, they are electrical engineers, and they are control engineers as well. So they know the whole thing. So their capability of thinking is wider than the traditional control engineers. And the traditional engineer, as we mentioned, these are the strong engineering which you have to be combined together, mechanical, electrical, and software. So what is mechanical? Mechanical is related to motion. Anything when you want to move, that is mechanical. Electrical, of course, we understand how we transfer the electricity. It can do heating, it can do motion. When we are running an electrical motor or a fan, so this is basically electricity is being converted into mechanical work. And the software is basically, it is the model which gives the decision what to do, whether to switch off, whether to switch on, to run it faster, to run it slower. So that actually basically comes from the software. And in the software, basically, we need extensive coding. So this is an example of prehistoric control system. Here is there was no electrical system, but they used to control speeds. So this is known as the Watt's fly ball governor. So you can see it is dated back to 1769. So almost 300 years ago. So capability of modeling of big system for optimal configuration is an important requirement for a mechatronics engineer. So what is modeling? So modeling, I'll discuss immediately. Modeling is basically when we represent physical things knowing its relationship with each other. So if you see a mass, spring, or a damper, so I have a mass, I have a spring, and I have a damper. So we call this is a mass spring damper. So how is going to move? If I apply a force and that's release, so it is going to vibrate. How is going to vibrate? This we can express mathematically. If we solve the equation of the mathematics, that gives us the solution. So at the first place, representing the system, this is basically the representation of a car, how a car is moving, vibrating in the vertical plane. In that case, the mass of the car is here. The supporting springs is damping, and it has shock absorber, which is called as damping coefficient. So this is the way how they are related. And you can see this doesn't look like the car. It is an abstract form, but this is really which actually we are looking for. Then we can relate this because this is a mechanical system, and the mechanical system is modeled by basically the Newtonian mechanics, which is F is equal to ma. So you can see the F is equal to ma is a mathematical model of this system. So this is the system, and this is the mathematical model of the system. Then A we can write as dx dt dot. So this you can write further d square x dt square. That means if we integrate this equation, we can relate how x is changing with respect to time. So that we call the simulation. First, we come up with the system representation, which is how many masses are there, how many springs are there, how many links are there, how they are connected to each other. And then we derive the mathematical equations out of it, and then we solve the equation. So we have the physical model, we have the mathematical model, and then we have the simulation. And out of the simulation, actually, we can tell how it is going to behave. So once we have the modeling successfully done, actually, we can predict how it's going to behave, and we can make that product. And when you go to model, it's not simply mechanical system. Mixed system may be involved. In one system, there are multiple elements, and they can be fluid system, thermal system, electromechanical system, like the video just I have shown. You can see in that model, we need all these things. We have the heating, so we have the thermal system, we have liquid material flowing, so we have the fluid system, we have the mechanical links moving, so we have the mechanical system, and we have the electrical motors. We have to run the electrical motors, so we have the electrical system, and electro-hydraulic system. Basically, for cooling purposes, we are sending the liquid into the system. So those are electro-hydraulic systems. So you can see how involved are mechatronics systems. Here are some examples of mechatronics products. Today's camera. Then this is the MEMS products instead. It's a micro gear. Here, whatever you can see, the diameter of this gear may be just 1 millimeter or half a millimeter. That is the diameter. So you can imagine how small is the teeth. Okay. Then high-speed train is this is the smallest one, and this is the biggest one. Today's autonomous cars. These are examples of big mechatronics products. And mechatronics product has got a wide range of classification. So I'm not going to discuss all this classification. Maybe it will be uploaded. So we have class 1, which is primary mechanical products. Class 2, traditional mechanical system updated with internal devices with electronics. Then case 3, system that retain functionality of the traditional mechanical system, but the internal mechanism is replaced by electronics as digital watch. So we had the mechanical watch before, now we have the digital watch. Class 4, mechanical electrical technologies through synergistic integration. So which you can see what we call Segway, or the what is called autonomous car, the robots, like this. I think this is already I have shown the physical system. So as I mentioned, so here you can see how we model. So this is basically modeling of a electromechanical system. So this part of the system is, we can say this is the electrical part of an electrical machine, where you have the resistances and inductors and everything. And that is the central core, which has got the moment of inertia, and we have the gearbox, and we have the load bus. So this is the physical system. Then out of this physical system, we have our mechanical mathematical model. And to have a mechatronic system, one of the important elements which is basically control. And control always depends on 2 elements. One is sensor, another is actuator. Sensors which can sense. Camera is a sensor. Infrared sensors to detect temperature. Then ultrasonic sensor to detect distances. And there are so many sensors available. And actuators, it can be electromagnetic actuator. It can be electrical motor as an actuator. And there are smart actuator as well now is available, which is called SMA, then piezoelectric, which are applied for specific purposes. And when we do handle these 2 elements, sensors and actuators, specifically for the sensor, we need the signal analysis, because sensors, the way we believe it is going to give the proper output, but unfortunately not. The output of a sensor may be very rough. Then we need to do some filtering to have the proper output, which is actually required to make the decision, to give the decision to the actuator for its action. And computer and logic systems. So of course, after this sensors and actuators, they are linked to the computer, which gets the decision from the sensor models, and then it gives the input to the actuators for its motion. And also we have the data acquisition. You see, this is a ECG. So here we have the sensors. We are collecting the data, and out of this data, you are actually giving the diagnostics. So what is the condition of the heart of the person? That is also a mechatronics device. And here is a very simple way we are talking about mechatronic systems. So here you can see we are talking about the autonomous car. So autonomous car basically, as if it is like a human, it can see what is in front and what is at the back, or what is on the two sides, the road lanes, everything, and accordingly it can move without accident. So what we need the input to our car. So this is the car following at the back is our autonomous car. So when it is moving, it has to trace the car in front and it has to trace the car at the back. And then accordingly, it has to make that decision. So how the decision comes, so you can see here. So this is basically we have the computer inside the car that actually gets all this information, and then it decides how to run the car accident-free. The problem with mechatronics engineers, even after 50 years, it is almost 50 years mechatronics has been introduced, but still many people do not know who are the mechatronics engineers. And this is one of the hurdle you have to overcome when you go to the job market, because they don't know you. They know the mechanical engineers, electrical engineers, even though know the today's software engineers, but they don't know what is mechatronics engineer. So as a mechatronics engineer, you have to express yourself, and you must have the ability to handle basic mechanical, basic electrical, and extensive software. Software must be one of the core elements, because for control you need the software. In our department, we actually classified some of the elective courses for mechatronics engineers, because mechatronics, you can understand from the integration, it integrates almost anything on Earth. So for a single person to have the master of all these disciplines is almost impossible. So we had come up with some classification, so that after you learn the core, you take the elective, so you can say I have the specialization in these areas. So if you want to have a computer and control, then you need any of these three courses from this stream, whichever you like. So accordingly, you can improve your specialization. Or if you are electrical and electronics, basically who are basically instrumentation engineers in the companies, you can take courses from here. You can see biomedical instrumentation, remote sensing, electrical power system, microelectronics, and mechanical and automation. Autonomous robotic system, robot hardware, fluid power system, industrial robots, thermal and fluid machinery, and vibration. So these are the courses. So this, but the way our structure currently we are executing, not necessarily you have to take these three courses from any stream. If you are interested, you can take these three courses from the stream that we want to combine. Now, as it looks, mechatronics engineers are master of all trades. Now, it is not that easy to be master of all trades. So what must be your core competency? That is, if someone asks, okay, all mechatronics engineers will be able to say, okay, I can do this. So what is this? One is design. What is design? Design means when some specification is given to you and you develop some system which follow that specification. Like someone says, okay, I want to fly from Kuala Lumpur to New York within 1 hour. So make a device for. So specification is just from Kuala Lumpur to New York. Now it is your choice what you want to design. You want to design a rocket, you want to design a plane, you want to design a car, you want to design a ship. Okay, but to fulfill this specification, you must have prior knowledge. If you say I want to make a ship and the ship will go from Kuala Lumpur to New York in 1 hour, it is almost impossible. That means without the proper knowledge, you do not know how to design. And then hands-on, you don't need to know the hands-on like the technicians, but you must have the minimum hands-ons. Those are basic things you can fix. And for mechatronics engineer, you have to combine both of these. Okay, so traditional engineers, basically they say civil engineers, they mostly can do design. For civil engineer, it's not possible for them to do the work of a mason, which is hands-on. Okay. Similarly, for mechanical engineers also, they are mostly concentrated on design. Doing this heavy stuff, lifting, fixing together, that is also impossible. But for us, there is a fixation which is basically on the control. Controller is not a big stuff which you can handle. So if you can be hands-on on controller implementation, that will be excellent for a mechatronics engineer. And you can say, if mechatronics engineer can do design and handling, so what's the traditional engineering are going to do? Yeah, mechatronics engineer, we are teaching how to combine the things and to design. And after you design, each of the component has its own way of designing. That is basically designed by the traditional engineers. Like, you need to know, your design says you need a 100 kilowatt electric motor. 100 kilowatt electric motor is not so easy to make. This can be built by the electrical engineers. So you just give the specification, I need 100 kilowatt electrical motor. The weight of the motor should not be more than that. Now, electrical engineer had to scratch his head to come up with that particular motor. Similarly, we need so big gears or small gears, then we pass it to the mechanical engineers. So we can say the mechatronics engineers are type of managers in engineering. So they manage the whole design and then they distribute the job to the traditional engineers. So system design should be the core competencies of mechatronics engineers, and traditional engineering discipline will be doing their usual core business. So sometimes when we talk about the mechatronics, often we believe mechatronics is robotics. Actually, mechatronics is not robotics. Robotics is in mechatronics. Other than robotics, there are a lot of other stuff in mechatronics. The first video I have shown you, that is not a robot. That we call a injection molding machine. But that is a mechatronics stuff. And it is there in manufacturing processes for years, and it has been improving a lot because of the mechatronics way of designing. And if you look at this, the design of this running shoe, okay, so this running shoe will give the minimum, what is called, stop on the body, and the runner will be able to run faster. So this is not a robot, this is a mechatronic stuff. So it has got its sensors, it has got its actuators, and this looks like a robot, but this is a part of a robot basically. This is we call the exoskeleton. Here there is a demarcation line between robotics and mechatronics, but anyway, still it is not that very clear what is robotics and what is mechatronics. But as long as it is mechatronics, it can be in robotics as well. But not necessarily all robotics we can specifically tell mechatronics, because robotics has got some social component nowadays. If you talk about the software, so software has got a lot of software in it rather than hardware. So it actually extracts the data from the network, and accordingly it makes the decision and it tells this. So those are basically the IT people's job. But making a robot which can work successfully, which can do work successfully, that is basically the mechatronics. So here you can see an exhaustive list of what is robotics and what is mechatronics. Smart devices and system automation should be the focus of mechatronics graduates. So when you are learning, so what is your target? Smart devices and automation. So the washing machine, dishwasher, clothes washer, these are basically automation of manual washing. Okay, so this is a mechatronics device. So how to integrate the different subdomains in a washing machine? You have the fluid going into the system. You are heating the water. You are rotating the drum. You are checking the what is the cleanness of the water and deciding how long to run the machine and when to open to take the stuff out of the machine. So you see there are decision issues, there are sensing issues, and there are actuation issues. And the device is smart. You put the stuff inside, you just switch off, and you just keep okay, go, and it will finish its job stuff. System modeling and design, instrumentation, interfacing should be the core competencies of the graduates. Instrumentation, which is basically related to sensor and how to read out the sensors and how to connect this sensor with the computer or multi-controller. That is we call the interfacing, because if the sensor is not integrated with this system, then you cannot make it mechatronics. And mechatronics is just not robotics, as I said. Robotics is just one part of the mechatronics. So here you can see an example of a mechatronics. We call the Segway. So this is a smart device. It can sense what you want to do. Accordingly, it will do the steering. Accordingly, it will speed up and slow the speed and do the braking. This is robot. You can see. So our traditional vehicles has got the scale wheels, but with the wheels, basically we can just fly on the smooth roads. But if you want to go to rough terrain during the winter, you want to go to the hilly areas, so we have to go for the rugged version. So here there are some big dog, the name of this robot, I think developed by Boston Dynamics. So here phonics, Mars lander. Okay, you can say prosthetics. So someone lost his hand, so we are developing devices to support him or her. So it can interface with the nervous system so that when he or she is intending to do a particular activity, so the robotic hand can follow. Unmanned vehicles, underwater robots, everything are under actually mechatronics devices. Okay, and mechatronics is now becoming more prevalent everywhere because of the cost-effective microprocessor and microcontroller, as well as sensors and actuators. So the new ideas are being developed, MEMS and adaptive control methodologies. MEMS we call the microelectromechanical system. Those who have seen what we call glucose measuring element for the diabetic patient, we call glucometer. This is the MEMS device. And inside your phone, here is a sensor we call the inertial sensor, which is basically accelerometer and gyroscope. This is a MEMS device. It's very small. It needs a special technology for its fabrication, and also design you need a special software. Real-time programming method, networking and wireless technologies, virtual prototyping and testing, and so on. So where it is going to lead to, we don't know. Now I am just giving in relation to your course that while you are going to in the course, I think you have to run a small vehicle as a robot. You have to control its steering and everything. But as engineers, just putting the thing together and doing trial and error is not actually the way we work. We work pen and paper at the first place. We design the thing. Then we tell, okay, if you operate within 5 to 10% error, it will work. So yeah, if you want to design a car, uh, autonomous car, so how much force you need to drive it. So these are the components of the force you have to apply. Fa, we call the mass into acceleration. So you have to accelerate it, so it will go under the mass into acceleration. Then Fr, this is the frictional resistance. Frictional resistance can come in many ways depending upon. One is mu into n, which you studied. Another is the what you call rolling resistance, which is the radius of the wheel hub. Then Fd, which is called the drag force. This is, there is a drag coefficient, and v square by twice g. So if you know the drag coefficient, so when you start, our cars are not moving that big, and here we don't need to design it, but Fa you must have to know. And in this case, we calculate the speed, and if you know the velocity, then we can calculate the amount of force. And mostly the cars we are running, they have this force very big because it is running at 80 to 120 kilometers per hour. So if you square the corresponding meter square, it is a very big term. So it contributes significantly to the force that you need to apply to run the car. And it is a Fg. Fg is basically weight of the car. So this is basically W. So how the road is inclined, if you have a road. So this is your car. Okay, this is theta, and this is W. So you can calculate. Now this is the amount of force actually you need to run your vehicle. And how much power you need? So this is the calculation of the power. This is, it comes Ft, the velocity, and efficiency of your motors. Motors, those we use, their efficiency is generally 80 to 85%. Then you can get the, what is the power of the motor. And also we need a torque compliance. What is the torque? This is the torque calculation. You can see PT we have already calculated. So the mean velocity we know, then we can calculate. This is the velocity of the, what you call, the wheel. So then we can calculate how much torque is required, and to run a particular distance, how much energy you need. So you can calculate how long this vehicle can be on the road. Because nowadays these electrical vehicles are coming, autonomous vehicles are coming, all are being run by batteries. So if you do not have enough battery power, so you cannot be on the road for a long time. Okay, these are the under the same thing here. And now let me just introduce some elements of mechanical systems, specifically in the mechatronics, because you have been introduced to the different elements like mass, spring, and damper, I mentioned before. But inside we have many things to connect. And what are these? We call the tendons, wires, or chains. You can understand if you say chain, timing belt, you understand. So this is an element basically to transfer rotational power from one location to another location. This is a tendon, and then it has its advantage, but it has a disadvantage as well. Tendon may get stressed, and generally for big power, we cannot apply these tendons. Chains, you already have seen in the motorbikes, in the bicycle, we use the chains to transfer the power from the what is called pedaling wheel to the rear wheel. And they have the advantages and disadvantages. Okay, disadvantages basically and wear, tear, then what is called heavy, like this. So here you look, this is an example of a robot. So when we make the robots, robot has got its hands and links, how they are connected. So here you can see, this is a robot. When we are running this link, we do not put the motor here, we put the motor here. Because if you put the motor here, then it becomes heavy, because motors by default are quite heavy. So that is why we shift it here. And similarly here, to run this system, we are using a mechanical system because this is a heavy robot. So just to using the normal motor will not be enough. So we have this mechanical system. Some other robots, we just use the tendons or the pulleys. And so you can see everything you are using the pulleys and belts, and we are running our system. Gears. Okay, so here you see the gears, and in your lab, the gears you will be using, the motors you will be using, they are basically some are with gears, some are without gears. The motors, those are coming from the power window, they are with gears. And the purpose of the gear is basically to change the speed ratio or the torque ratio. Also to change the direction of motion. So here you can see these are two gears. If this is rotating in this direction, we transfer this motion in this direction. This is another one. So these are tuned shafts. So when we are rotating in one direction, this is rotating 90 degree, but not intersecting, non-intersecting. But here you can see these are intersecting. This is the shaft. If you extend, they are intersecting. And also we need sometimes to make linear motion to rotation. So we have these gears. When we have this kind of assembly, the gear, toothed gear, we call it pinion, and the horizontal element with tooth, we call the rack. Rack pinion is basically it goes in both direction. If we drive this one, it will be moving to and fro, and if we move the rack to and fro, the gear will be rotating. Okay, when we drive our system, we have positive motion drive and friction drive. So when we're driving stuff with gears, we call the positive drive. That means when one gear moves, the other gear must move. This is called the positive drive. And the other we call the frictional drive. Frictional drive is basically like belt and pulley. That is, if you rotate one pulley and the other pulley you hold, you will find the belt and the pulley is slipping. So this is because of the frictional drive. It depends where we need which one. Frictional drive is basically for, in many cases, for safety purposes or small amount of force when we need to transfer, we use the frictional drive. And for positive drive, specifically, we do not want to slip. In that case, we use the positive motion. And in between, we have the idler gear, basically to change the direction of motion. I think we mentioned here. Here, we can see the driver and follower. So we want to run it. But if we put next to each other, this and this will be rotating opposite each other. But if we put it in between another one, so this and this will be rotating in the same direction. So this is just helping us to make the change in the direction. So this is we call the idler gear. Okay, there are worm gears. Worm gears are basically special type of gears. This is power can be transferred from in one direction, from the other direction you cannot do. If you rotate the worm, the nut will move. But if you want to move the nut, it will not move. That is basically the way we design it. So this is for the safety purposes. When we design the lift, in the lift, the motor is connected with this assembly, so that if for some reason if the motor fails, then the lift head will not fall. Okay, here are just examples of other harmonic drive. Basically, these are used for high gear ratio, specifically for motors using the expensive robots, because these gears are very expensive compared to the traditional gearings. If they're small, other gears where it can cost maybe 100, 200 ringgit, the similar one with a high transmission can cost 5,000, 10,000 ringgit. Here you can see example of a washing machine. This is a front loader washing machine. Let me see. There is a it's a front loader washing machine. So what this machine has got, you see the door has got some sensors. So when you switch it on, it can sense you have switched on, so it will not allow you to open the door if there is water. So front loading machine has got this kind of issues. Then you have connected to the water mains, and then you have the controller when to switch on to the water to go in and go out. Then we have heater inside. Then we have the rotors to rotate the drum, all these things. So this is an example of a mechatronic device, and this is being controlled. You have the control panel, so this is being controlled by a microcontroller. So microcontroller actually carries all the programming, which you have to run for washing different types of clothes. If you want to wash cotton, then you have the one setting. If you want to wash silk or wool, then you have another setting, and accordingly, the sequences will be maintained by the microcontroller, and the sensors and actuators will behave in the following these instructions. This is just the internal structure of the drive. So you can see here, this is a motor, and motor is connected with a bell drive. Okay, so when you put the bell drive, that is, the power is not that very big. This is the first thing, and second, it is often when you have the big load issues and where the output can stop, we actually put this bell drive so that the motor cannot stop. Otherwise, for some reason, you have overloading of the drum and you want to drive the motor and motor doesn't move. In that case, the motor may burn. But if you have a belt and pulley system, if it doesn't move, just it will sleep and the belt will burn. This is the vertical loader in a similar way fashion, and there are reasons why you have the vertical loading machine and why you have the front loading machine. Front loading machine are generally expensive compared to the vertical loading machine. But vertical loading machine is very easy. You can open anytime, take some cloth out, add some cloth in. These are the advantages, but the disadvantages, vertical loader machine basically spoils your cloth. So these are less expensive and easy to make. These are the wheel robots. There are a lot of structures of wheel robots. Now we can see that people are making the Mars robots for to be autonomous vehicle in the Mars. So this you can see how do we do. This is the simplistic structure of one of the robots. This is on the floor, and if you run these two motors, if you move in the same direction, they will, with the same speed, it will be moving in the same direction. If one is slower, then it will just rotate. If we make this wheel slow and this wheel faster, then the robot will move in the slower wheel direction. So this is the slow. This is the first. But if you reverse the motion, then it will just rotate on the same spot. So this is the advantage of this two motor driving without the steering. So it can steer and it can move the wheel. These are other versions pipe crawler. If you want to have the devices to move inside pipes for inspection purposes or for collecting debris from inside, so you can have this kind of robot. We have the grid propelled, so we need the threaded wheels rather than normal wheels. I think that is the end of this introduction to mechatronics. So mechatronics is a very huge area, but whatever you are learning, that is the fundamental and core. If you can learn this fundamental and core with the hands-on, hopefully you will be successful in your real life career. Okay, thank you very much. Assalamualaikum.
Assalamualaikum warahmatullahi wabarakatuh. Thank you to